In July 2022, scientists expected the James Webb Space Telescope to confirm our textbook origins of the cosmos. Instead, it found 6 galaxies so massive, so early, that experts now call them universe breakers, objects that simply shouldn't exist only 500 million years after the Big Bang. These galaxies defy 99% of our models, as if you'd found a towering redwood in a sapling's garden. The stakes couldn't be higher. If the James Webb Space Telescope is right, our entire understanding of how the universe began is on the line. What could possibly create galaxies that break the rules of reality? And what secrets does this cosmic upheaval hold? After its first deep field exposures, the James Webb Space Telescope returned images that stunned even veteran astronomers. In a patch of sky barely the width of a grain of sand held at arm's length, Webb's NIRCam revealed 6 galaxies shining with the luminosity of the Milky Way. Yet their light began its journey when the universe was less than 700 million years old. These objects, identified at redshifts between 7 and 9, stood out not for their faintness or youth, but for their sheer scale, each one containing billions of stars, packed into systems that should have taken billions of years to assemble. The data, drawn from the telescope's first photometric surveys, suggested masses rivaling our own galaxy, compressed into a cosmic instant. Researchers expected to find scattered, primitive star clusters. Instead, the universe's earliest chapters seem to host mature, sprawling galaxies. Far too soon, far too big, far too bright. For a field built on gradual cosmic growth, these findings were nothing short of a shock. The standard model of cosmology predicts that galaxies should grow slowly, starting small and merging over billions of years. Yet these early giants defy that logic. For a galaxy to reach Milky Way scale in less than 700 million years, nearly every available atom of hydrogen would need to turn into stars. Almost perfect efficiency. That's not just rare, it's unprecedented. Joel Leja, one of the lead researchers, put it bluntly. We shouldn't have found galaxies like this at all. The numbers demand a rethink. If these galaxies really formed so quickly, it's as if a redwood tree appeared in a garden planted last week. The physics of star formation sets hard limits. Gas clouds can only collapse so fast, and not all material turns into stars. But the Webb data imply a conversion rate close to 100%, something never seen, even in the wildest starbursts today. The anomaly isn't just about one galaxy. It hints at a broader problem, one that could ripple through every timeline in cosmology. Measurements of the universe's expansion rate have long relied on 2 rival yardsticks. The first uses the cosmic microwave background, with the Planck satellite finding a value of 67.4 kilometers per second per megaparsec. The second, led by Adam Rees and the SH0ES team, uses Cepheid variable stars and Type 1a supernovae to build a local cosmic distance ladder, arriving at 73.0. The difference between these two figures is not trivial. It's a gulf that has now surpassed 5 standard deviations, the threshold physicists use to declare a genuine discovery. Webb's entry into this debate was expected to provide a decisive verdict. Its infrared vision allowed astronomers to re-examine over 1,000 Cepheids, eliminating the crowding and dust that had plagued previous measurements. The result? The James Webb Space Telescope. These readings for these galaxies matched Hubble's almost exactly, with a formal difference of just -0.01 magnitudes. This means the higher local expansion rate stands, and the tension with Planck's early universe value remains unresolved. Meanwhile, other teams using Webb's data to calibrate the tip of the red giant branch, and carbon stars have reported lower expansion rates, closer to 68 or 70. The result is not a neat reconciliation, but a deepening puzzle. Every method, when pushed to its limits, insists on its own answer. Webb has become the impartial referee, confirming the split rather than closing it. Cosmologists have begun to look beyond the boundaries of our own universe for answers. One radical proposal suggests that our cosmos is not unique, but only one bubble in a vast multiverse. In this view, the early universe may have experienced a brief surge of extra energy, what theorists call early dark energy, just before atoms first formed. This extra push could come from our universe brushing against others, or from a phase transition that briefly altered the rules of physics. The mathematics behind these models shows that even a fleeting injection of energy, lasting just a few 100,000 years, would shrink the sound horizon imprinted on the cosmic microwave background. That, in turn, would let the universe appear to expand faster today, lifting the predicted Hubble constant closer to the values measured by supernovae and Cepheids. Bayesian analyses now show that early dark energy, if it made up just a few % of the universe's total content at the right moment, could bridge much of the gap between the Planck and SH0ES results. Some versions of this idea even predict subtle ripples or gravitational wave backgrounds, potential fingerprints of cosmic bubbles colliding. While direct evidence for such collisions remains elusive, the models have gained traction because they fit the numbers where standard cosmology falls short. The possibility that our universe's expansion rate might be set by events beyond its own horizon has forced physicists to reconsider what counts as a complete explanation. For now, these speculative scenarios remain at the frontier, offering a glimpse of how radical new physics could be hiding just out of sight, waiting for the next breakthrough observation. Roger Penrose proposes a universe without a true beginning or end, one that cycles endlessly through epochs he calls aeons. In his view, each aeon begins with a Big Bang and expands until all matter decays and only energy remains. At this ultimate stage, the geometry of space and time can be stretched or conformally mapped, so that the infinite future of one eon connects seamlessly to the birth of the next. The crossing point between cycles erases the old universe's entropy, allowing a fresh start. This conformal cyclic cosmology stretches the cosmic timeline far beyond a single Big Bang, offering the possibility that structures from previous eons could influence what we see today. Penrose's team searched the cosmic microwave background for unusual hot rings, each about 3 to 4 degrees across, that might mark the final moments of black holes from a previous universe. Using Planck and WMAP data, they reported clusters of these so-called Hawking points, their positions matching across both maps. Yet, debate continues. Some researchers argue these circles could be random noise or artifacts. If genuine, they would be the first fingerprints of a universe before our own, waiting for confirmation from future missions. In 2022, the James Webb Space Telescope revealed 6 galaxies so massive and mature, existing just 500 to 700 million years after the Big Bang, that they directly challenge the standard model of cosmology. These universe breakers, confirmed by JWST's NIR, CAM imaging, at redshifts between 7 and 9, defy predictions of how fast galaxies can form and grow. Alongside this, JWST's measurements deepen the Hubble tension, showing a persistent gap between different methods of measuring the universe's expansion rate. While Nobel laureate Roger Penrose's theory of a cyclic cosmos and the debated Hawking points in the cosmic microwave background offer potential explanations, no consensus has emerged. Key questions remain. How did these galaxies assemble so quickly? Does our universe's timeline need rewriting, or are new physical laws required? As of today, the evidence forces scientists to reconsider core assumptions about the universe's history. The search continues, but one fact is clear. The James Webb Space Telescope has not solved the cosmic puzzle. It has made it deeper and more mysterious than ever before.